The next alumnus that I'd like to introduce is George Zimmerman, class of '69. Actually, went out of order a little bit, sorry, George. George, excuse me. George, you're being recognized for your contributions to society through your science and technology accomplishments. George graduated from Harvey Mudd College with a degree in physics in 1979 and went on to earn a, what did I say?
69.
Yeah, I'm sorry. What did I say? I'm sorry. 60. I'm sorry. Yeah. Good guy. In 1969, with a degree in physics, and went on to earn a master's degree in astronomy from the University of California, Berkeley. George has dedicated most of his career at Lawrence Livermore Laboratories, where he's made substantial contributions to national security by developing methods to analyze and model high-energy processes and atomic particle interactions. The result of his research led to the development of the LASNEX inertial confinement fusion computer program, which is used to design laser fusion targets and analyze experiments. He has developed numerical methods to accurately perform integrated simulation involving laser absorption, magnetohydrodynamics, atomic physics, and the transport of photons, neutrons, and charged particles. George is a leader in his field, as his contributions led to the development of models for equation of state, charged particle and photon transport, opacity, magnetic field generation, and again, hydrodynamics. So George has quite a stimulating presentation, and please join me in welcoming George
So it's wonderful to be back here. It has been 45 years again since I gave a lecture at Harvey Mudd. It was a senior project, and it was in computational physics. So I have stuck it out. I don't think computational physics was a career when I was at Harvey Mudd, but as it turns out, it worked out well for me, and so I want to share it with you. So let's start with talking just a little bit about computers. Everybody remembers this one. This is an IBM 1620. It was in the basement of the building over there. It isn't there anymore. You had to check out a key to use it. The 20 in the name 1620 stands for 20,000 memory locations. And each one of them stored a decimal digit. Decimal, you say. I thought this was a computer. Don't they work in a binary system or something? But no, this one was decimal. Notice also the nice little switches and lights and things like that. You could actually look what was in any given memory location if you wanted to. So let's see. So what else about that? This thing did multiplies by table lookup. It did its floating point in software. And as a result of all that, it ran at about 1 kiloflop, 1,000 floating point operations per second. The laptops that you're carrying around, this one right here, is about 1 million times more powerful than that. And we'll talk a little bit about where that came from. But this machine was a whole lot faster than the Monroe calculators in Thomas Garrett Hall. Right up there, I think on the second floor of Thomas Garrett Hall, Monroe calculators. It was just amazing. I spent spring break writing programs for the fun of it on this machine in Newtran. Yes, Henry, it was Newtran, not Fortran at that time. And I never expected that I would spend the rest of my life doing the same thing, doing what I love and getting paid for it. It was really marvelous. So what's a Monroe calculator? Yeah. Well, we took the cover off of this one for you engineers in the crowd so you could figure out how it works. This thing is an electronic calculator. That means it has a motor so that those levers and things can move around really fast. And if you set it off to do a square root, the whole room would shake. So the next 40 years after I graduated, the 40 years that coincided with most of my career, we saw a real computer explosion. This is Moore's Law, one of the versions of it. There are lots of them. This is the number of transistors per integrated circuit or something like that, and how it grows by a factor of 2 every 2 years. So that's 1 million over 40 years. And there are other versions of this like bang per buck and computer and things like that. The other things that happened during that same time are that computational physics became the third pillar of physics, right along with experimental and theoretical. was not the case when we started this thing, but it happened. And I was lucky enough to have it happen while I was out there doing it. So being lucky and timing is important, right along with being prepared and working hard and things like that. Will Moore's Law continue? I don't know. But everybody that's betted against it in the past has lost, so I wouldn't do that. Right near the top of that curve are the components that went into this machine. This is Lawrence Livermore National Laboratory's Sequoia machine. It is a 16 petaflop machine. That means there's 10 to the 13th of those 1620s inside of it, pretty much. But it's not just speed. I mean, most of that, a lot of that is coming through more processors. There's 1.6 million processors in there. And a lot of the difficulty with a machine like this is to figure out how to use all 1.6 million processors on the same job usefully and not just have a bunch of them sitting idle. The fellow at the left in this figure is Fred Streitz, and he's an HMC alum from physics, I think, in 1983. And he's basically in charge at Livermore of the unclassified high-performance computing. I can't remember all the titles he's got, so I'm going to say it that way. But he has led teams of people to 2 of the Gordon Bell Prizes in 2005 and 2007. And Fred tells me that he's not the only one from his family to graduate from Harvey, but that there are in fact 4 in his immediate family. So I think he probably deserves an award for that as well. So enough on computers. I now want to talk a little bit about big science. I was lucky enough to work on 2 projects in big science in my life. One of those is inertial confinement fusion at Lawrence Livermore National Laboratory. And the other one is a traveling wave fission reactor at TerraPower in Bellevue, Washington. Both of these are, what I mean by big science is that it takes very large teams, interdisciplinary teams working together over decades. Actually, the project with TerraPower has only been going on 7 years now, but it'll be more than a decade before we get much more done. The other thing is it takes a lot of money to do these big projects. The project on the left, the inertial confinement fusion, is Department of Energy funded, and the project on the right is Bill Gates funded, mostly. There's other contributors as well to the project. So the other thing about big projects like this is they need great big computer codes, multi-physics computer codes. Some of that falls naturally from the fact that they're expensive, these projects, and so you want to kind of get it right before you build all the big equipment. And so understanding it well with big physics code is the way to do it. So what's a multi-physics code? Here's one, the one that I worked on for 45 years, I guess now. It's called the Lasnik's code. It involves lots of different physical processes. Each of those little ovals there has a different thing in it, like hydrodynamics or atomic physics or laser absorption, different process. All the arrows and things, the things that make it, you want to call it spaghetti code, those lines and things, are interactions between these things. Each of the different processes may have its own time scale. And so writing a code that can do all these things simultaneously and stably in a computer without going crazy is one of the tricks that we have. The other thing that's notable about it is that each of those ovals has 5 or 6 different ways to do the same thing. And this is important for cost accuracy trade-offs, so you can run quick calculations with a cruder model, and also for self-checking, so you can use a more advanced model to check the accuracy of a crude one. So, and let's see, the next slide is my first paper, and I believe it's actually the most cited paper as well. And I'm among 4 authors on that, and I was just a computer jock. The other 3 guys actually knew what was going on at this time, because I was just a young kid. The idea here is to take isotopes of hydrogen, heavy isotopes of hydrogen, deuterium and tritium, in a liquid drop, shine lasers on it exactly correctly in such a way as to compress the hydrogen to 10,000 times its normal density. And that's quite a trick, of course, and then to ignite it and get fusion reactions out. So in this paper, we predict that we could get break even. That means equal energy, fusion energy out compared to laser energy in, at about a kilojoule of laser light. Well, We're now over a megajoule of laser light, and we haven't gotten there yet. But I absolutely am certain that with 10 megajoules, we will do it. So I don't think the 10 megajoules will be coming, but so be sure, you know, it's all right to go out on a limb. Let's see, the next slide shows the National Ignition Facility, also lovingly known as NIF to those of us at Livermore. This is a picture of the building, and there really are not 3 football fields on the top of the building. Those are just photoshopped in to show you the size of things. The game here is to take energy and compress it both in space and time. So this thing is going to be a 500 terawatt laser pulse that it delivers. That's 1,000 times the energy generation capability of the United States. But it's only going to put out the 500 terawatt for a very short time. Okay, so it draws energy off the grid in a order of minutes in time, and then delivers it to the laser glass, which then puts it into a laser pulse of about 20 nanoseconds in length. So very much compression in time to get all that energy in. And then we want to compress it in space as well. So we take those 3 football field size of equipment, generate the laser pulse, and put it in this 1 centimeter size gold can. The lasers have to go through the laser entrance holes at the end of the cans. They shine on the inside of the hole rim. These are called the hole rims. The energy there is absorbed, heats up the surface layers at the inside of the can. They generate X-rays, which flood the can and then impinge on the capsule inside of it. At that point, the surface layers of the capsules begin to blow off, and the rocket effect from that blow-off drives the rest of the inner parts of the capsule inwards. Again, we're trying to reach densities like 10,000 times normal density. And the reason for doing that is not just to get density, it's to get rho r. It's column density that matters. And if for a given amount of mass, the way you get high column density in a sphere is to compress it up in density. And the reason you want column density is in order to get ignition, the alpha particles that are produced by some of the deuterium and tritium reactions need to deposit their energy and heat the matter in order to get more reactions going. So that's the way you get an explosion or a bootstrapping effect. But it's important to get rho r, or column density, to do it. So this will work if everything's done perfectly. Well, what does that mean? It means perfectly shaped laser pulse in time. It also means essentially perfectly spherical implosions. That's the whole reason that we did that indirect thing with generating the X-rays and everything, was to create a more symmetric environment. When we calculate it, we get things like this for a 3D hydrodynamic calculation of an implosion like this, where we put on the initial perturbations that were actually on the capsule and did things as well as we could. Now you can see that's not a perfect sphere, but that's actually good enough to get essentially the same number of reactions as you would in a purely spherical case. But if the hydrodynamic instabilities are a little worse than we're saying they are, then you could get fingers going through it and holes in it and so forth, and the thing just won't work at all. And so far, we have not gotten ignition. Okay? 18 months ago was the completion of a national ignition campaign. It was sort of a political thing, and Livermore failed to get ignition in that time. Since then, we've taken a step back and done somewhat easier targets where we weren't trying for such high compression. The worst thing about, to me, was not that we didn't get ignition by 18 months ago, but that the calculations we were doing didn't agree with the experiments. You know, I mean, that's my thing, is the calculations, and we weren't getting the right answers. Now that we've backed up and have gotten somewhat simpler problems to run, we are agreeing with calculations. I mean, the experiments really are reproducing with simulations, and there's every reason to believe that we can find a path from where we are now to ignition, or at least understand why not. So, the other thing you could do with the National Ignition Facility is rent it out as a movie set. And that was done a couple of years ago when they made Star Trek Into Darkness. So the other big science project that I was involved with over the last 7 years now is to try to use depleted uranium to produce energy. In this yard, storage yard, depleted uranium, by the way, is just the leftovers from uranium enrichment. It's the part that the light water reactor people didn't want. They can't use it. It's just U-238, or lovingly called D-38 for depleted 38. There's enough uranium, if you could use it, there's enough uranium in storage yards like this to power US households for 700 years. Okay. And at the end of that time, or somewhere during that time, we will be, in fact, it's already happened that people have figured out how to remove uranium from seawater. And so one of the things you can do once you run out of this storage is to start removing uranium from seawater. And that should power global energy needs for about 1 million years. So that's a whole bunch. And so what do I mean by global energy needs? But, you know, who knows what we're going to need in 1 million years, right? So what I mean by that is 10 billion people, each using the same amount of power that we use right now, just to put a number on it. And you might think, okay, well, what's going to happen after that, after those 1 million years, you use up all the uranium in the ocean? Are you worried about that? Well, don't worry, because as you're drawing it out, the rivers are resupplying the oceans with it, taking it off the land. And there's enough uranium in the Earth's crust to power us at that level for 1 billion years. So solar may be cleaner and safer, but it is not more renewable than fission. Okay? 1 billion years is as good as it gets. So how are we going to do this? How are we going to get this energy out of this depleted uranium? This is the stuff that the light water reactor people don't want. So first I have to do a little lesson on fission. There are 2 kinds of fissionable isotopes that are important in producing energy. One of them you know about is the fissile isotopes. These are uranium-235, uranium-233, plutonium-239. And they just require that you add a low-energy neutron to it, and it immediately splits apart, releases energy, releases 3 or 4 more neutrons, and you're done. One of those neutrons goes off and creates another one of these things, and you have a chain reaction. There's another kind of isotope, and U-238 is one of those, that is called fertile. And what happens to the U-238, which is at 9 o'clock in this picture, is a neutron is absorbed by it, but now it doesn't fission. It just becomes U-239. But U-239 decays into neptunium-239, and then it decays to plutonium-239. And plutonium is a fissile isotope. So now you add a neutron to that, and you've gotten your fission process just like in a light water reactor. But the trouble is, it took you 2 neutrons to do that job. In the light water reactor, it only took 1. And you're getting about the same number out, about 3. So to make this game work, you have to be really stingy with neutrons. You can't throw them away, you can't let them leak out. Because for every 3 that you build, you got to have 2 left to do work for you. So the original design, original concept of a traveling wave reactor is shown here. This is just a stick of this depleted uranium. You want a 50-year reactor, you get 1 length. You want a 100-year reactor, you just double the length of the thing. It's that simple. You do have to start it some way at the left end, and that's going to take some U-235 or something to get it going. But after that, it will breed the plutonium-239 and burn it. So these are called breed and burn reactors. There are a bunch of neutron losses in this thing. The spent fuel behind them, half the neutrons are going to go backwards instead of forwards. And so there's a bunch of neutron losses that way. But for a physicist, this design works just fine. You just put, you can put this in your computer and calculate it. It works great. Unfortunately, there was a bunch of engineers involved in this project as well. And they said, oh no, there's gravity, so you have to have material strength properties and other things in there to hold the uranium up. And also you're going to need to cool it unless extract the energy from it. So that requires a bunch of pipes and things like that. By the time you put all that stuff in it, you got enough other neutron absorption that now the thing doesn't go. So we thought about getting a new team of engineers, but instead of that, we went ahead and redesigned the reactor. So as that one is traveling wave, this is more like a standing wave reactor. The cylinders, the blue things here are fuel assemblies, just look a lot like in real reactors, except they're just depleted uranium. The reaction's going on the center of it, and it's radially, the reaction is trying to radially go out. But we don't let it. We keep moving the fuel in. spent fuel at the center, we remove it, throw it away, well, actually store it someplace, and then replace on the outside more depleted uranium. So this is a standing wave version of the traveling wave reactor, and it doesn't lose those neutrons out the back end because you've removed the spent fuel. But it's a little more complicated to use. Okay. Let's see. And then, of course, there's a lot of different kind of calculations that have to be done to do this thing. One of them, which you know, of course, is neutron transport. Where do the neutrons go in there? And then also what happens to all the fuel and everything in there. So we call that transmutation of all the isotopes. There's going to be fission product buildup. And for example, you can see up there that some of those blue rods are higher, have different lengths than others. So we are including in this calculation things like buildup of fission product gases that makes the fuel expand and grow in length, so forth. So there's a bunch of things like that, fluid dynamics, things like that. And then there's also safety calculations. Here's sort of a full-up engineering reactor design of that. And there's a lot of shielding material, which you can see in gray there, floor. But you want to analyze, what's the safety situation with people walking around on top of that floor. So a lot of complicated calculations to do. So that's pretty much it. I wanted to say that, of course, to do those calculations, TerraPower also has to have a computer cluster. This one only has about 4,600 CPUs instead of 1.6 million at Livermore. But it's got lots of cool lights and things like that. So, thank you.